At the end of this video, you should be able to define a fluid, distinguish a gas from a liquid, determine the magnitude of the buoyant force exerted on a floating object or a submerged object, and explain why some objects float and some objects sink. Solid, liquid, and gas are three different states of matter. You have studied motion and its causes using solid objects. In this unit, we look at the mechanics of liquids and gases. Think of liquid water and helium gas. One property they have in common is the ability to flow and to change their shape. Gases and liquids are fluids because the atoms or molecules are free to move past each other. Solid objects are not fluids because they cannot flow. Solids have a definite shape. Liquids, like solids, have a definite volume, but unlike solids, liquids do not have a definite shape. Gasoline, which is a liquid, changes its shape when poured from one container into a lawnmower tank. If there is a gallon of gasoline in the container before you pour, there will be a gallon in the tank after you pour. But gases are neither a definite volume nor a definite shape. When a gas is poured from a small container into a larger one, the gas changes its shape to fit the new container and also spreads out and changes its volume within the container. In general, density is a measure of a quantity in a given space. The quantity can be anything from people or trees to mass or energy. Mass density is mass per unit volume of a substance. In this course, when the word density is used, what is really being measured is the mass density. Mass density is the mass per unit volume of a substance. It is often represented by the Greek letter rho. The SI unit of mass density is kilograms per cubic meter. The densities of different liquids, solids, and gases tend to change, and the densities sometimes change very little with changes in pressure. But gases are compressible. The densities that are listed in the table provided to you in your textbook are the values at a stated temperature and pressure. So be sure to note the stated temperature and pressure. When temperature and pressure change, the density of the gas can change by quite a large amount. So solids and liquids have standard densities, but gases do not.
Mass density is the mass per unit volume of a substance. The SI unit of mass density is kilograms per cubic meter. Gold is among the densest materials found on Earth. A balloon filled with gold would weigh as much as 20 water balloons. Water is the standard of density. It has a mass of 1,000 kilograms per cubic meter or 1 gram per cubic centimeter. Gases are much less dense than liquids or solids. However, they can expand or contract with changes in temperature or pressure, so it is important to note the conditions at which a measurement is made.
Buoyant forces can keep objects afloat. If you have ever rested on an air mattress, rested on an air mattress that's in a swimming pool, you have experienced a buoyant force. A buoyant force is an upward force exerted by a liquid on objects that are immersed in or floating on the fluid. A buoyant force keeps you and the air mattress afloat in the swimming pool. You may have noticed that objects feel lighter underwater than they do in air. The weight of an object immersed in a fluid is known as the object's apparent weight. Remember, the buoyant force acts upward, opposite the force of gravity. So the net force acting on an object submerged in a fluid is smaller than the object's weight. In the case of a heavy object, such as a brick, its apparent weight is less in water than its actual weight is in air, but it still may sink in water because the buoyant force is not sufficient to keep it afloat.
Consider a brick that can be submerged in a container of water. As the brick sinks, the water level rises and water begins to flow through the spout into a smaller container. The total volume of water that is now in the smaller container is the displaced volume of water and is equal to the volume of the brick. The brick will experience an upward buoyant force equal to the weight of the fluid that was displaced. This is known as Archimedes' principle. Legend has it that he thought of it one day when he spilled water on the floor while getting into the bathtub.
Archimedes' principle describes the magnitude of a buoyant force. So the set of images on your screen here show how to find the volume of a brick using water displacement. The displaced volume of water is equal to the volume of the portion of the brick that is underwater. And so in picture A, a brick is lowered into the container of water. In part B, the brick displaces water. This water flows into a smaller container. In part C, when the brick is completely underwater, the volume of the displaced water can be found because D is equal to the volume of the brick. Archimedes' principle can be thought of as any object in a fluid has an upward buoyant force that equals the weight of the fluid displaced by the object. Using m sub f to represent the mass of the displaced fluid, Archimedes' principle can be written as follows. Now, whether an object will float or sink depends on the net force acting on it. This net force is the object's apparent weight. Now, we can apply Archimedes' principle and use m sub o, stands for object, to represent the mass of the submerged object. The gravitational acceleration, little g, is factored out. From the equation for density, remember that m is equal to rho v, or mass is equal to the density, the mass density multiplied by the volume. So the expression can be rewritten as follows. Note that in this expression, the density of the fluid, rho sub v, and the volume of the fluid, v sub f, refer to the displaced fluid. For a floating object, the buoyant force equals the object's weight. Now imagine a cargo-filled raft floating on a lake. There are two factors acting on the raft and its cargo: the downward force of gravity and the upward buoyant force of the water. Because the raft is floating in the water, the raft is in equilibrium, and the two forces are therefore balanced, as is shown on the screen here. For floating objects, the buoyant force equals the weight of the object. And so we can represent the buoyant force acting on floating objects as is shown here. You don't need Archimedes' principle, again, water displacement, to find the buoyant force on a floating object if you know the weight of the object. Imagine that the raft that we just showed has a hole and sinks below the water's surface, as was shown on the previous slide on the right. As the volume of the raft decreases, the volume of water displaced also decreases, which makes the magnitude of the buoyant force decrease. This can be written as net force is equal to rho sub f multiplied by volume sub f minus the density, rho of the object multiplied by the volume of the object, all multiplied by acceleration due to gravity. Because the raft and cargo are completely submerged, volume sub F and volume sub object are equal and are replaced by simply volume. If we factor out volume, we can end up with a net force being equal to rho sub F minus rho sub O, all multiplied by volume multiplied by acceleration due to gravity. So if the object's density, meaning rho, is greater than the fluid density, the net force is negative, meaning downward, and the object sinks. If the object's density is less than the fluid density, the net force is positive, meaning upward, and the object rises to the surface and floats. If the densities are the same, the object hangs suspended underwater. And there is a simple relationship between the weight of a submerged object and the buoyant force, which is shown at the bottom of your screen here. Force of gravity on the object divided by the buoyant force is equal to the density of the object divided by the density of the fluid. And you can use this last expression at the bottom of your screen to solve buoyancy problems.
A raft that is floating is in equilibrium. That is, the net force on the boat is zero in the vertical direction. The downward force of gravity is exactly equal to the upward force of buoyancy. If we add cargo to the raft, its weight increases. The raft will sink downwards. As it sinks, the buoyant force increases due to the additional water displaced. The raft will once again be in equilibrium. More cargo adds more weight, which requires more buoyant force. Any object that is floating has a buoyant force on it that is exactly equal to the weight of the object. It is possible to sink a raft if its total weight grows too much. To sink a raft, the total weight of the raft must be greater than the weight of an amount of water equal to the whole submerged volume. In other words, an object will sink in water if its density is greater than the density of water. Buoyancy continues to act when an object is underwater. The apparent weight of the object when submerged is just the true weight of the object minus the buoyant force.
At this point, you should be able to satisfy all four objectives listed at the beginning of this video.